Liz.
Thamban, you all right?
All good. It's too early for you.
It is a bit. I'm gonna try really hard to wake myself up a little bit this morning, but yeah, bear with me.
Hi, Sachin. Sachin, can you hear us?
Yes.
Good. Thank you.
Good morning. I am here. I was checking that's on. I'm just gonna.
Hi, Dr. Krishnan, can you hear us?
Yes, yes, I can.
Thank you.
Thamban. Yeah. So am I audible clearly?
Yes, you are.
Thank you so much.
There's one more panelist has to come. Then we could talk.
Can I quickly share my slide? Just
Right. Please do that. Yeah.
Sorry, could you try share screen mode, please?
Is this okay?
Yeah, can you put them in the slide mode, the presentation mode?
It is in the slide mode only.
But it is not now for us. Okay.
It's not.
Maybe because you haven't shared the entire screen. Instead of that, you must have shared one file.
Okay. So
Maybe you can leave and try quickly. Yeah. Come back again and then share the entire.
So I will start sharing. So what do I do? I
Share there must be multiple choices, isn't it? Share the
share basic, advanced. Okay, basic.
let's try that.
Okay, control to select multiple windows.
Yeah. Can you do it at now, full screen mode?
Yeah, just a minute. Is it okay?
No, it's not. Mintu, is there any suggestion for him?
Sir, could you try Control F5? Just F5?
F5 is it?
Yes.
Control F5.
No problem, sir. Could you go to that slideshow written on the top? Home,
Yeah.
insert, design, animation, slideshow.
Just a minute. Okay, I pass the share and yeah. Where do I go? Share sound, share. Just a minute. I'm going to the share screen. I clicked on the in the bottom share screen.
Okay.
And then I click on the
Maybe you can simply click that multiple participants can share simultaneously.
yeah, now let me see. Now this is yeah, okay. Is it okay now?
No.
Is it okay now?
No, still we can't see the entire screen. We can see a screen, but not in the presentation mode.
Sir, there may be issue because your PowerPoint is not activated.
Excuse me?
Sir, your PowerPoint is, I think that version is not activated.
Okay.
Do you have a PDF copy of it? I think that also should be solve the problem.
If I have a PDF, it will work. You think so?
Yeah, if you don't have animation, it should work, I suppose.
Okay, let me see that. Okay. Just a minute. Sorry. Is it share screen?
Yep.
No, it is just
Share screen. Yep.
now I have to. Is it seen now?
I think it should be coming. It's you are not clicked it. Did you click it?
Yeah.
So you have to open the file and then click on share screen and select the file.
Okay. I have to open. I've opened the PDF file.
Now you're clicking share screen, sir.
Okay. Yeah. Is it okay?
Yeah. Now you could use the view mode, view the top
mode. Okay.
Yeah, the full screen mode.
Okay.
Yeah,
Is it
I think
okay?
that's fine. So that should be fine for you.
Yeah.
So it works fine. Thank you.
Okay. Thank you.
We are still waiting for Kyle. Can you just check someone whether he's available and can be put inside? Kyle Clem.
Oh, thank goodness.
Hi.
I've been watching everything, but not not
Oh.
able to talk to
Yeah,
you.
sorry. I think I probably did not recognize you. So I'm sorry about that.
Oh, no, it's okay. I figured I was doing something wrong.
Dr. Thamban, I'll do one thing. I'll send my PPT to you just in case that I have a problem.
Right, just mail me, right, in case it's required.
Okay. So should I try to share my screen?
You can just check it, yes.
Should be all good. All good.
Yeah.
You can see it.
Can you put them in presentation mode?
Yes.
Yeah, it works.
Great. Okay.
List may not require it, I think, isn't it? You're doing it on a daily basis.
Sorry,
You don't need to check it, isn't it? You do it on a daily basis. I suppose.
I think I'm all right.
Not required. Yeah, we just got 1 more minute to start. Okay, so let me try to say this. Actually, the whole idea is actually that we have these 2 chat box. One is the chat box, which is basically interaction among the analysts, as well as the team which is available there. And the actual chat for the participants is using the Q&A chat box. So, but however, we can also set some messages to the people who are there in the audience through the chat box. They can only see it. They cannot anything type. They will only be typing at Q&A chat box. So just to confuse and avoid the confusion among the participants as well as the, the panelists. Shall we start? Just 1 minute. Yes, so can we start? So let me start. Good morning, good day, and good evening to wherever you are. So welcome. My name is Thamban Meloth from National Center for Polar and Ocean Research, situated in the beautiful state of Goa. And in coming 2 hours, essentially, we will have a session. I will be rather trying to convene as well as moderate this session on teleconnections between the poles and the tropics. As most of us appreciate that in a rapidly warming world, understanding the linkages between the tropics as well as the polar regions are going to be more and more crucial for improved predictability of the climate system. In fact, recently, most of us have heard about this, in fact, rather astonished by the fact that actually the extreme heat waves and extreme precipitation events are happening in the whole Antarctica as well as in the Arctic. Sometimes similar at the same time, but maybe connected to different systems. So, for example, recently we also heard about this atmospheric rivers becoming more and more features, more frequent and more stronger, reaching to Antarctica, bringing large amount of highly warm, moist, air, which is leading to sometimes warm as well as the high amount of precipitations. So therefore, actually, we do understand understanding the tropical as well as the polar teleconnections going to be crucial in the coming days when we project the future changes. We have nearly about 50 participants already listening to us. So I think there's a good, I would say, good communication which is going to be the people. We have today 4 experts from a varied spectrum of the subject, starting with observation people to modelers as well as to the proxy climate researchers, from who was exclusively working in Antarctica to those who are working mostly in the tropical region, trying to look for exchanges between these 2 systems. So first, we will have a series of small talks by these experts. Rather, I would be starting with Kyle Clem, then it would be Sichen Lee, then it's Liz, then it's going to be Dr. Krishnan. So then we would also have an opportunity for people to raise questions. The all audience, my request is to you that use the Q&A chat box, not the chat box. The chat box is for the panelists, but however, you can use the Q&A box to raise your questions or important things you want to raise to the panelists, which would also become a food for us later discussion when the panel discussion starts. Every questions may not be answered immediately, but it may be there may be a collective discussion about those questions later at the later session. So please be very patient. At the same time, do keep asking questions. So to begin with, I start with Kyle. I just also have to just read out what the Kyle is essentially trying to understand the Antarctic and the tropical teleconnections, who has been recently very famous for actually pointing out this South Pole, rapidly warming South Pole, and its connection to the rest of the world. So Kyle works at the University of Victoria in New Zealand, I suppose. I'm sorry if I'm mistaken. Because I'm unable to see the screen actually where I can actually read out your things. I'm sorry about that. But I think I would request you to also introduce yourself and you can directly start presenting your presentations. Thank you, Kyle.
Okay, thank you, Thamban. I thought Zishan was going first. Let's get this going. Can you see my screen?
Yes.
All good?
Yes.
You can hear me. Okay. Well, thank you very much, Thamban, for this invitation to be part of this symposium with some amazing experts here, and just excellent work organizing this. Sorry, I have to get rid of this. I still hide video.
Are you looking for the pointer?
No, I'm trying to hide floating meeting controls. There we go. You'd think after all this teaching I would have Zoom under control, but I don't.
That's fine.
Yes, there we go. So yeah, thanks to the conference organizers, I know how massive of a job it is to organize a large international conference with everything else that you have going on. And the program looks amazing. And just thank you very much for pressing on with these important conferences during everything that we're going through. It's a shame we can't be there in person, but at least we cut down on our carbon footprint. So I will be talking about some recent work that I've done with some colleagues looking at temperature and surface melt extremes on the Antarctic Peninsula. And I am more broadly interested in how the tropics can trigger extreme climate events, extreme high temperatures, and how this can lead to surface melting on the ice shelves where temperatures get above freezing. And I'm interested both in multi-decadal timescales. I need to start my timer, but also I've become more interested recently in these convective events, these bursts, these short-lived events, such as those associated with the Madden Julian Oscillation, that can trigger these wave trains over the course of a few days to a week, maybe 10 days, completely alter the atmospheric circulation and produce conducive circulation patterns that can bring in short-lived but intense heat and moisture in the form of atmospheric rivers at times, and how these extreme events can impact the Antarctic. So before I start, just a quick plug that SCAR has a really awesome portal down here on the bottom, so environments.aq. So the Antarctic Environments portal, there's some excellent summaries in there already. They're intended to be easy access, relevant for policymakers, but also relevant for anybody who might not be an expert in a certain discipline in Antarctica. And there's going to be 3 sea ice summaries being published in shortly here that my colleagues and I wrote, and there's lots of other good ones on there too. So I encourage you to check it out. They're really great summaries. So, okay. So Antarctica, a land of extremes, it seems, and it covers multiple timescales. So a lot of my work as a grad student was on interannual variability, and then this shifted to multi-decadal variability, some of which is highlighted here. So some examples of extreme multi-decadal variability in this case. So the Antarctic Peninsula here on the left was once the most rapidly warming place on the planet. And then that suddenly stopped, and all of a sudden it started cooling. And so these rapid dramatic swings in multi-decadal variability are quite common in the Antarctic. Here in the middle was some work that Thamban noted. The South Pole, which we thought was largely isolated perhaps from warming while the rest of the globe was warming. It was even cooling a bit, shown down here in the bottom during the 1970s and 80s. It underwent a rapid shift to strong warming after the 1980s, and that's been highlighted by consecutive record high warm years. So again, another example of these rapid multi-decadal shifts. And Antarctic sea ice continues to surprise us as well. While it was increasing, we then see rapid changes to record lows and rapid decreases. But we also see this in extreme events. And so 2 of Antarctica's warmest temperatures ever recorded have occurred since 2015. And these temperatures are remarkably warm, and they are well above freezing, and they can lead to very intense surface melting. So this includes the 17.5 degrees Celsius temperature that was observed on the Antarctic Peninsula on the 24th of March, 2015. We thought, wow, that was very warm. And then just a few years later, that was surpassed by 18.3 degrees Celsius in 2020. And then the records in the extreme events, they just keep coming. Just in the past year or so, the South Pole has its most severe cold on record. Temperatures in East Antarctica, 70 degrees Fahrenheit above normal. Antarctica reaches another new record low sea ice extent this year. So the records just keep piling up in the Antarctic. And I'm interested in what drives that variability. And it's important because I'm particularly interested in the ice shelves, which fringe about 75% of Antarctica's coast. And when you get these extreme warm temperature events, it can lead to very strong surface melting. And on the Antarctic Peninsula, for instance, this surface melting can lead to ice shelf collapse through a process called hydrofracture, where the surface melting, it ponds and it trickles down through rifts and cracks, and it expands when it refreezes, and it mechanically breaks these ice shelves apart, leading to a dramatic collapse, which we've seen on the northeastern tip of the Antarctic Peninsula since the mid-1990s. And then to the south, so this will be the focus of the work that I present today, the much larger Larsen C ice shelf on the eastern Antarctic Peninsula has been observed to be thinning in recent decades. And in July 2017, a massive chunk broke off, forming the world's largest iceberg at that time. And so I'm curious as to what the fate potentially of Larsen C is moving forward. Is it the same as Larsen A and Larsen B, which collapsed in this dramatic fashion? It's more stable. However, we don't fully understand what may have caused the collapse of these ice shelves further to the north. And so we know the mechanism, and the Antarctic Peninsula consists of a steep mountain range that extends north-south, perpendicular into the westerlies. And this provides a conducive environment for foam warming. You get these warm, dry winds, which we'll talk about in a moment, that come down onto these ice shelves, and they can lead to short-lived but very intense warming events that lead to this surface melting that can lead to this collapse. And so understanding what drives surface melt in this area and extreme high temperatures was the motivation of some recent work. And so Jonathan Willey published a very nice study earlier this year that showed ice shelves on the Antarctic Peninsula. Their stability is closely tied to the occurrence of intense atmospheric rivers. And again, this is linked to this phone mechanism, which leads to very strong warming on the eastern side. But atmospheric rivers, they found in this study, lead to intense conditions in almost all aspects that drive ice shelf stability. And so when you get on the right here, when you have intense atmospheric rivers, this is the percentage of temperatures and various parameters that can weaken ice shelves that was occupied by 99.9 percentiles. So how much of this area was occupied by extreme melt, extreme temperatures, extreme swells during intense atmospheric rivers. And we can see, or what Jonathan did very well was showing that intense atmospheric rivers lead to extreme aspects of all mechanisms that can weaken ice shelves. And so atmospheric rivers not only lead to all of these different mechanisms, but the moisture that they bring is a key ingredient to get very strong phone, because the more moisture you have that's ascending the windward side on the western side of the peninsula, the more latent heat can be released, the slower the cooling, and then the more dramatic the warming on the eastern side. So much of our knowledge on what drives phone variability on the eastern peninsula is confined to meteorological stations that are located on the very northeast tip of the Antarctic Peninsula. So particularly Esperanza and Marambio stations shown here on the right. And these are only long-term continuous temperature measurements. And these stations are closely tied to variability in the SAM. So shown here on the left are correlations with Antarctic meteorological stations, their temperature with the SAM index. And so while positive phases of the SAM lead to strengthened westerlies that generally lead to cooling around Antarctica, on the peninsula, because of this phone effect, when you strengthen the westerlies traversing them, it actually leads to warming on the eastern side. And so we've generally thought that the collapse of ice shelves on the eastern Antarctic Peninsula may be tied to a strengthening of the westerlies associated with the positive trend in the SAM. And the seasonality works because the SAM has underwent a positive trend associated with strengthened westerlies during the summer season, which is when temperatures are most favorable for surface melt. But we don't have proof that the westerlies or the SAM also lead to surface melt on the Larsen sea ice shelf further south. And so in this study with my colleagues here, this was published just a few weeks ago in Nature Communications. We used surface melt data on the Larsen sea ice shelf from a high resolution polar WRF simulation. And this was run from December 1991 to March 2015. And with this simulation, we extracted surface melt on the Larsen sea ice shelf. And we started just by investigating what drives variability in surface melt down here, where we don't have a long-term measurements. And shown on the right are correlations with sea surface temperature, outgoing long wave radiation, which gives us a proxy for the presence of deep tropical convection, which would be in the blue here. So negative outgoing long wave radiation is associated with deeper convection and colder cloud tops. And then the stream function and 500 hectopascal height fields on the bottom left two panels. And then on the right are some time series with some particular or some key large scale climate indices. And this study was done over the summer melt season from December through March. And on the top left, Larsen sea surface melt we found was associated with positive sea surface temperature anomalies off the equator in the southeast tropical Pacific, perhaps El Nino-like, but no significant sea surface temperature anomalies in the equatorial latitudes. The correlations with outgoing long wave radiation were intriguing because we found that although we don't see a significant relationship with sea surface temperature, we do with enhanced deep convection here on the eastern edge of the South Pacific convergence zone. And correlations with the stream function field and the 500 height field revealed a Rossby wave-like feature emanating from the central tropical Pacific near this enhanced convection. And this pattern leads to, or is associated with, a very strong area of high pressure over Drake Passage, and that would be associated with enhanced westerly flow over the Antarctic Peninsula. And we didn't see a significant relationship with ENSO indices or the SAM, but we did see very strong correlations of over 0.6 with convection in the central tropical Pacific and pressure over the Bellingshausen Sea and Drake Passage. So to get a Rossby wave response from convection, you have to be in an area of climatological ascent. And so some great work by Lachlan, Cope, and Conley in 2006 showed that no matter what type of surface heating anomaly you put in the tropics, if it lies in an area of climatological descent, you can't generate a large-scale ascent response that can trigger a wave train. And so contoured here are the negative omega climatologies for the austral summer season, which are areas of large-scale ascent, overlapped with the SST and OLR correlations with Larsen sea surface melt. So these significant sea surface temperature correlations do not lie within an area of climatological ascent. However, the correlations with enhanced deep convection lie in a very favorable region here in the South Pacific convergence zone of large-scale ascent, and they would be conducive for producing a Rossby wave response, and the propagation would then be tied to the background circulation. And similarly, if we look again at the Larsen sea surface melt correlations on the left, and we compare those to correlations with outgoing long wave radiation in the central tropical Pacific, they look very similar. They're associated with an enhanced anticyclone over Drake Passage, very strong, and this would lead to enhanced southwesterly flow. And then on the bottom, both enhanced surface melt and deep convection in the central tropical Pacific lead to anomalous moisture convergence on the windward side of the peninsula and divergence over the Larsen Sea area. And this is a classic phone feature where you have moisture convergence on a windward side, divergence on the eastern side, and that would produce conditions favorable for phone warming on the Larsen Sea ice shelf. It was surprising, though, to see a strong connection to the tropics during summer because the background jet streams are generally not conducive for Rossby wave propagation into high latitudes. And that's because during the summer, the southern hemisphere mid-latitude jet dominates through the middle latitudes, and it extends across the entire southern hemisphere, and you lose the subtropical jet. And so the subtropical jet, which is really only present in winter, serves as our Rossby wave source. And then there's usually a duct in the mid-latitude jet over the South Pacific that allows Rossby waves to propagate through. And so if you have a continuous jet across the Southern Ocean, this would act to refract waves that would come out of the tropics and prevent them from reaching Antarctica. However, we performed a sensitivity experiment where we generated a deep convective anomaly. So here's New Zealand, the Antarctic Peninsula. So these are the precipitation anomalies that the model generated. This was with CESM version 1.2. And contours show the anomalous stream function compared to a control run. And then on the right shows the anomalous 500 hectopascal geopotential heights. And if we start on the right, this convective burst actually leads to that pattern that we saw in the correlations with a strong ridge or high pressure over the Bellingshausen Sea and Drake Passage, the very, very favorable feature to get phone warming and surface melt on Larsen Sea. And it also is associated with a very large, elongated in the north-south direction mid-latitude cyclone. And together these would be favorable for transporting very warm, moist air from lower latitudes down to the Antarctic Peninsula. And this is not SAM-like, so the circulation response to this convective forcing is very zonally asymmetric, which is a good feature if you want to generate strong poleward moisture fluxes. Back to the left here, the vectors show the anomalous stationary wave flux. And we get strong poleward wave fluxes out of this convective anomaly. And not surprisingly, we get a lot of refraction off the mid-latitude jet. However, Rossby wave sources allow these Rossby waves to continue propagating. And the shading here shows the climatological jet stream, which is continuous across the Southern Ocean during summer. But an important term of the Rossby wave source is divergence, which is maximized at the exit and entrance regions of jet streaks. And we found an important jet streak to the north of the Amundsen Sea low, in the entrance region where divergence would be locally maximized, we can get Rossby wave propagation through the mid-latitude jet into the Bellingshausen Sea to impact the climate of the Antarctic Peninsula. And we saw, am I out of time?
Yeah, unfortunately, we are running short of time. So are you able to, in 1 minute or so?
Yeah, definitely. And we saw the same feature during the two record high temperatures that I mentioned earlier. So a deep convective burst triggered a wave train that propagated through the mid-latitude jet into high latitudes. And the last thing that I'll end on is what the circulation told us is that we get very strong poleward heat and moisture flux. And we found that both Larsen Sea surface melt and increased convection in the tropical Pacific are associated with enhanced frequency of intense atmospheric river landfalls. And so when you have deep convection, you get an increase in intense landfalling atmospheric rivers. This is just what triggers the convection. We'll stop there. But yeah, so what's interesting is that on seasonal and long-term timescales, the background jets play a very important role at modulating teleconnections. But on synoptic timescales, if conditions come together right, tropical teleconnections can make their way down to Antarctica really during any season, and they can drive these extreme events, often in the form of atmospheric rivers. So I'll leave it there. I'm sorry for going over. I saw 19 minutes, but
Yeah.
I started my timer too late.
Thank you so much, Kyle. I think it was very fantastic and interesting, very hot topic that currently is on discussion. We don't find any immediate question for you, but I think we would be having for the panel discussion coming up. Just a housekeeping note to the participants. I can see that the large number of participants have increased now, and for all of those actually who will come later, I just want to say that actually you please use the Q&A box, not the chat box, but the Q&A box to raise questions or suggestions or comments what you like to for the panel to be discussed later, or even be answered. Okay, so we move on now to Sitan Lee, who is from Institute of Atmospheric Physics in Beijing, who is a member of International Commission of Polar Meteorology, and also read the recent exactly work which is showing off now. It's a huge amount of people. He put people together to discuss the tropical teleconnection impacts on the Antarctic climate changes. Over to you, Sitan. Thank you so much.
Thank you, Professor Meloth. Did I share my screen or?
Yes, you did.
Yeah, thank you. So it's really a big honor of me to introduce our work in this conference. So last year, many professors, we worked together to write a review paper about tropical polar teleconnection and its impact on recent Antarctic climate changes. And there will be 4 parts in this presentation. The first part is why we are so interested in the tropical polar teleconnection. A short answer is it may help to explain the rapid and asymmetric changes around Antarctica. About Antarctic climate changes, so many of rapid climate changes happen around Antarctica. One of them is the rapid glacier melting, and it may contribute to the global sea level rise, and we're really concerned about it. If we look at the spatial distribution of this glacier melting, we find most rapid glacier melting happened around the West Antarctica rather than other areas, especially 2 famous glaciers, the Breeze Glacier and the Pine Inlet Glacier. And in 2018, Shepard wrote a paper in Science. It's talking about it quantified the glacier melting around different areas of Antarctica. We'll find since 1990s, the entire Antarctica released about 3,000 gigatons of fresh water. That's the purple line. And when we look at the West Antarctica, the green line, it just contribute more than 90% of the total freshwater release. Similarly, when we look at the surface air temperature warming, we find that the most rapid warming also happened around the West Antarctica and the Antarctic Peninsula, especially before 2010. When we look at the East Antarctica, the warming trend is negligible. When it comes to the Antarctic sea ice, it becomes more complicated. So when the Arctic sea ice keep retreat during the past several decades, it agree well with the global warming trend. But the Antarctic sea ice before 2015, it increased a little bit. It's considered as the Antarctic sea ice paradox. Only except some area around the West Antarctica, the Amazon Sea, the Bellingshausen Sea, and the Weddell Sea, we find some sea ice loss. But after 2015, the Antarctic sea ice experienced the sudden sea ice loss. When we summarize the climate change around Antarctica, first, the most rapid glacier melting happened around the West Antarctica, the Pine Inlet Glacier and the Breeze Glacier. release about 1,000 gigatons of fresh water each. When it comes to East Antarctica, only Totten Glacier, it started to release fresh water after 2010, only about 300 gigatons of fresh water since then. And the most rapid surface warming happened around the West Antarctica and Antarctic Peninsula rather than East Antarctica. And when we come to the Antarctic sea ice, before 2015, the West Antarctica sea ice, the Amundsen, the Bellinghausen, and part of the Weddell sea ice experienced a rapid loss. Other area, the sea ice has been increased. And after 2015, the Antarctic sea ice experienced a sudden loss almost everywhere. The main driver of Antarctic climate change, one of the main driver is, of course, the global warming or the increase of the concentration of greenhouse gas. But since most of the rapid climate changes happened around the West Antarctica, this zonally asymmetric change cannot be fully explained by the regional related forcing caused by the increase of the greenhouse gas. So, and many of recent studies indicate that the atmospheric circulation changes, especially the deepening of the Emerson sea low, it may help to explain this zonally asymmetric climate changes, help to explain the sudden climate changes around the West Antarctica. And the circulation changes can be further attributed to the tropical polar teleconnections. That is the main reason why we are so interested in tropical polar teleconnection. And second is, what is the tropical polar teleconnection, or what is the Rossby? A brief answer is that one of the main mechanism is the Rossby wave dynamics. When I start to learn the climate dynamics, my professor told me that the atmospheric bridge is usually, or the remote effect is usually referred to as like a climate variability over one region. It perturbed the atmosphere, it changed the circulation, and it propagates where basically the planetary waves to another area, change climate variability there. So for me, it's too abstract. And many times I feel it could be just a very weak effect. Until one day I realized that actually sound wave itself is the atmospheric bridge, or it is the remote effect. When we speak, so we perturb the atmosphere around us, we change the velocity and pressure, and it propagates through sound waves. Usually the sound of a human can only be propagated for less than 100 kilometers, but some mammals like whales in the ocean, the sound can be propagated for 1,000 kilometers, and it really communicate with whales 1,000 kilometers away. And in 1961, when Russia launched the most powerful nuclear bomb to Siberia, the sound generated by the bomb, actually it go surround the globe for 5 times. So the things that whether the teleconnection is powerful enough, or whether it can be propagated to very long distance away, it actually depends on the initial perturbation or the energy of this teleconnection. And in the climate system, the atmospheric teleconnection, the energy comes from sun, so it's much more powerful than the nuclear bomb. And usually so it propagates in a rotated sphere of the Earth. It actually regularizes the waves, making the wave propagate further than the sound waves. So here's the stationary Rossby wave. We have a schematic animation about stationary waves. It can really propagate like a wave, and propagate go around the Earth. then it's a brief introduction to how tropical polar teleconnection impact on the atmospheric circulation anomaly around Antarctica. So when people first realized that there's a tropical polar teleconnection, it's because of the extreme El Nino events in 1981, 1982. So when the El Nino happened, people realized that there's a climate variability or climate response all over the globe, and some pioneers like Hoskins, Crowley, and Mike Wallace, they reviewed the so-called Pacific South America and Pacific North American mode. That's basically stationary waves. The main idea is that the equatorial warming caused by the positive phase of ENSO, the El Nino, it can generate deep convection in tropics, and it can intensify the Halley circulation. And this adjustment, it can perturb the subtropical jet and generate stationary waves, propagate to polar region, and change the circulation there. Usually, El Nino events can generate the positive phase of PSA mode, which can increase the surface pressure around the Amazon Sea area. So because there's a low pressure system, so increase the surface pressure means we can weaken or we can shallower the Amazon Sea low. But that's what happened on interannual timescales. On decadal timescale, we have the Pacific Decadal Oscillation. The tropical polar, the teleconnection generated by PDO is quite similar to the what happened to the circulation, similar to the teleconnection generated by ENSO. So in the past 20 years, we experienced a negative phase of IPO, meaning that means that the tropical eastern Pacific, the surface temperature has been decreased. So the teleconnection generated by the negative phase of IPO is just the opposite to the positive PSA mode. The circulation around the Amazon Sea area has been decreased. The Amazon Sea low has been deepened by the negative phase of IPO. So we introduced the teleconnection from the tropical Pacific, but on decadal timescale over the Atlantic area, we also have a very strong multidecadal variability. It's called the Atlantic Multidecadal Oscillation. So here is the surface temperature of the North tropical and the North Atlantic from 1880s. When we remove the long-term trend, we have such a oscillating mode. And if we do like a 10-year smooth of this surface temperature time series, we will have a very clear oscillation with period of about 60 to 70 years. And in the past 40 years, so the positive phase of the Atlantic Multidecadal Oscillation together with the global warming trend it lead to a rapid warming over the entire tropical and the North Atlantic. The mean temperature change over the tropical and North Atlantic is about 0.6 degree in the past 40 years, but in some regional area, the warming trend is much faster. We do some regression and statistics. We do some regression MC analysis between the Atlantic and the southern hemisphere circulation, actually the sea level pressure around the Antarctica. And we also perform numerical simulation to drive the model with the tropical and North Atlantic warming. We find the tropical and the North Atlantic warming can generate a deepened Amazon Sea low around the West Antarctica. And we see some like a wave train-like pattern in this model simulations. But the problem is that the tropical Atlantic is quite close to the West Antarctica, but the stationary Rossby wave cannot propagate to the west. It can only go if the transatlantic, the Rossby wave trains generated by the transatlantic can impact on the West Antarctica. It has to go surround the Antarctica and finally arrive there, this area. We thus perform some idealized simulation. We find that it's true that the transatlantic induced teleconnection induced Rossby wave train. It can propagate to the south and to the east, go around the globe, and finally arrive the West Antarctica. We also do some diagnostic analysis, like based on the dispersion relation of the Rossby wave, and we find the jet system can help to reflect the wave and finally focus it on the West Antarctica. That's why the Rossby wave can keep the energy and propagate, go all around the globe. So right now we have that IPO can impact on the Antarctica, and the AMO can also impact on Antarctica. But what happened in the past 40 years? So here's the time series of AMO and the IPO. We find from 1980s to 2010, we have the positive phase of AMO, and from late 1990s to about 2015, we have a negative phase of IPO. Through numerical model simulation, we find that the positive AMO and the negative IPO, they can both deepen the MSCC low, although the area is a little bit different. So they work together to lead to a continuous deepening of the MSCC low. And another aspect of this story is that the IPO and AMO, they are not independent. Some recent work shows that the positive phase of AMO can drive the negative phase of IPO through tropical interbasin interactions. So then the whole story is that we have a positive phase of AMO. It generates long stationary Rossby wave trains propagate to the West Antarctica and deepen the MSCC low, lead to a low pressure anomalous low pressure center around the West Antarctica. The positive phase of AMO can also drive the negative phase of IPO with a time lag of about 10 years. And this negative phase of IPO can generate a negative phase of PSA mode, also deepen the MSCC low. And these two multi-decadal or multi-decadal oscillation, they work together, lead to a continuous deepening of MSCC low in the past 30 or 40 years. And what happened? So what happened to the Antarctic climate changes? What does this deepening of MSCC low impact on other aspects of the Antarctic climate? So we have the circulation changes like caused by the MSCC low. So the low pressure center in the south hemisphere is usually it is associated with the clockwise circulation around the West Antarctica. And this clockwise circulation will lead to a thermal advection from the Southern Ocean and South America, a warm advection from this area to the peninsula and part of the West Antarctica. It can help to heat the peninsula and the West Antarctica. But meanwhile, it transported a lot of very cold air from the inland Antarctica to the coastal area of the East Antarctica. It cools the East Antarctica. It agrees well with what we observed in past several decades. And meanwhile, this thermal advection can help to explain the sea ice redistribution. Most of the area, the sea ice has increased because there are a strong cold advection. But around the West Antarctica, because the warmer advection, we have a sea ice loss around the Amazon and Bellinghausen and part of the Weddell Seas. And the wind-driven mechanical forcing can also build a lot of linear around the East Antarctica. It also helped to increase the sea ice there. Meanwhile, the inland wind around the West Antarctica, it helped to melt more sea ice. The circulation changes can also drive the subsurface ocean. The intensified the deepened atmospheric flow, the intensified circulation can help the subsurface warm water intrusion to the front of the West Antarctic glacier. Can also help to melt or help to accelerate the melting of the West Antarctic glacier. And here's the schematic figure of how this teleconnection drive the recent observed Antarctic changes. We have intensified atmospheric low. It drives a warm advection to the peninsula and West Antarctica, hit this area. Meanwhile, it melt the sea ice. It drives a cold advection to the East Antarctica. It cooled the coastal area of the East Antarctica and increased sea ice there. It also helped to drive the warm water intrusion to the West Antarctic continent shelf, intense or accelerate the melting there. Here's the brief summary about how tropical polar teleconnection impact on Antarctica climate changes. So we have tropical decadal variability, including the IPO and AMO. It generates the stationary Rossby wave chains and deepen the atmospheric low. And through a series of atmosphere ice ocean interaction, this deepened atmospheric low, it hit the West Antarctica and cooled East Antarctica. They changed the sea ice and also intensified or accelerate the glacier melting around the West Antarctica. We also have some very brief progress, but because of time limitation, I will skip this part. Thank you so much.
Thank you so much, Shishan, for that fantastic discussion overview of the tropical polar teleconnections. We have plenty of questions for you, but I would start with maybe one or two of them because of the time limitations.
Okay, thank you.
One of the questions actually for you is that how much strength AMO Rossby wave train before it reaches the peninsula? How much strength do the AMO Rossby wave retain before it reaches the peninsula?
So sorry, the signal is a little bit. So how much of
the strength the AMO Rossby wave retain before it reaches the peninsula?
Before it
reaches the Antarctic Peninsula.
I'm not quite sure whether I understand it correctly. So do you mean how much of the energy of the Rossby wave?
Right.
So it's very interesting. We find actually is it two story. So where's my okay? So am I still share my screen or not?
Yeah, if you could explain, that's good enough. Because
okay, so actually, as because of there's maybe two aspects. The first is that the subtropical jet can help to keep the energy. So basically the energy will not be so the wave will not be dispersion when it go around the globe. And there's another aspect of the stories is because when the wave propagate to the West Antarctica, a lot of energy can be tracked from the mean flow because the jet becomes weaker at this area, and because of because of the climate dynamics, a lot of energy can be transported from the mean flow to the waves when the mean flow becomes weaker. So that's why the atmospheric low is so strong, or the deepening atmospheric low is so significant. It generates it perturbed by the tropical polar teleconnection, but it also gets a lot of energy from the jet structure.
Thank you.
Yeah,
there's one more question for you. I think if you could answer quickly, is it possible to quantify the impact of different processes acting on West Antarctic glaciers, melting of these glaciers? You mean to say whether teleconnections or is it due to the greenhouse gas? Are you able to quantify the different percentages?
Thank you. It's a very important question, and hard to answer. It's hard to quantify. One thing is that we can use the numerical model to quantify the impact from different areas to the deepening of MSCC low. So my feeling, my experience told me that usually the numerical model simulation, it can it's not the quantification of the numerical simulation not that accurate, but based on the numerical simulation, about 50% comes from Atlantic and a little bit less than 50% come from Pacific. That's how they contribute to the deepening of MSCC low. But when it comes to the glacier melting, it becomes very complicated, because the glacier melting is mainly driven by the subsurface warm water intrusion. So we did a lot of simulation using ocean model, and we find different under different conditions, the contribution from different basins. So it's like how to say? It's really hard to quantify it. So the atmospheric part is okay, but if you want to quantify the glacier melting, is too hard right now. Yeah.
Thank you, Sachin, for that
Thank you so much.
fantastic presentation, as well as answering those questions. We have more questions, but we move on now, but probably we will find better times there later on again further to discuss. We move now to Liz Thomas from British Antarctic Survey, who is also the head of the ice core research based climate studies at BAS, and who is also the lead of the Clivash 2K project of pages. And Liz is basically provide the context of how do the proxy data or the long-term climate data discuss this tropical teleconnections to Antarctica. Over to you, Liz. Thank you so much.
Thank you very much. And yeah, thank you very much for inviting me to take part in this symposium. And it's really, it's really great actually to join this symposium with the experts that we've got, because I've just had a fantastic overview provided to me for all of the teleconnections. And actually, I've really learned an awful lot from reading those recent review papers as well. So actually, it makes my job a little bit easier, because I can kind of now jump in a little bit onto the work that I've actually been doing using ice cores. So for my area of expertise, I suppose it's trying to look at these teleconnections, but actually taking them back further in time. So wanting to expand beyond just the short instrumental period and see whether these tropical teleconnections are maintained over decadal to centennial timescales, and whether there's a difference in the strength or the influence. So although I sort of put my talk title in here talking about the tropical Pacific, just checking, is that screen changing? Sorry, there we go. Okay, my screen was a bit slow there. It was actually fantastic just to see on those last slides there, actually, how we're kind of thinking about Antarctica down here in the bottom of our planet as being this sort of isolated landmass. But actually it's influenced by these different tropical teleconnections. And although I focus very much on the Pacific, I was going to sort of, point out that actually there's a huge amount of interconnection between these different basins. And so actually we need to be thinking about this not always as a single basin influencing a single region, but actually thinking about how these different teleconnections and different basins themselves are interacting. So the structure that I was going to give for my presentation was I was just going to do a really quick recap, because I was actually really hoping, and it's already been done, that there would be a really thorough evaluation of the teleconnections for Antarctica, and particularly for West Antarctica. So I'm just going to skip over that really quickly. And then what I'm going to move on to is looking at these teleconnections over the recent centuries and how ice cores can actually provide a way of us looking back further in time to explore the teleconnections between different regions. And finally, at the end, I'm just going to do a little plug to some new data compilations that we've been working on as part of the Clivash 2K working group, and hopefully sort of explore how that may be used and may have potential to look at this teleconnection over much longer time periods. So again, I'm not going to go through this because I just really wanted to put this up and say, we're really fortunate that we've now got this fantastic review of all of the tropical teleconnections and how it's impacting Antarctica. And so this is a really good base to start from. So I won't go into any of the detail, but I just wanted to put up on here, because my focus has been working very much on ice cores from the Antarctic Peninsula and West Antarctica. Obviously, my focus or direction, I've been looking pretty much into the tropical Pacific and how this teleconnection has been influencing the climate. But also, interestingly, it's looking now slightly more towards, actually, is there potential influence from the Atlantic as well? And we saw how these wave trains can actually propagate all the way around from the tropical Atlantic and have the same kind of influences on what's happening in the climate of West Antarctica, particularly coastal West Antarctica and the Antarctic Peninsula. So these were just some of the changes that we see from these different sort of ENSO-like patterns, or what we're seeing from the tropical Pacific, and how they compare. And essentially, I wanted to put this, just showing some of these figures from this review, because we're looking at changes in surface air temperature and looking at changes in sea ice, and also looking at changes in snow accumulation or surface mass balance. And those are the things that ice cores are really, really good at. Those are the things that we can use as reconstructions. So just putting into some kind of linking with, why it's important looking at the sea ice. So again, this is just, I'm just going to, cherry pick a few little examples really of things that were relevant. So this is by no means a thorough review, but just showing how some, how there's been some recent work looking at this Rossby wave teleconnection and how it's influenced changes in sea ice, particularly around, the rapid declines that we saw in 2016. But then also how ice cores have been able to look back at a slightly longer time period. And so this is the work from David Schneider, where they were identified in the ice core record, this sort of warm anomaly in around the 1940s, and how this was then linked to particularly changes in the tropical Pacific, and actually the anomaly associated with the El Niño event of 1939. So these are ways that some advances have been made in looking at ice cores to extend our understanding beyond just the sort of 1980s and the observational era. So what I really focus on is actually what's happening much closer to the coast of Antarctica. So a lot of the proxies that we see in ice cores in Antarctica, particularly for West Antarctica and the Peninsula cores, it's very much related to the changes in the Amundsen sea low. So we've heard a lot about it already, but this sort of quasi-stationary low pressure system that sits out in the Amundsen Sea. And actually we can see here this work of Scott Hoskins. It's got this sort of seasonal migration pattern. And this is what has a really massive influence on a huge range of the different climate parameters, looking at sea ice, changes in snowfall and temperature. So it's really understanding what's happening in here that's been my focus. But obviously the Amundsen sea low itself, as we've already seen, has multiple means of which these tropical teleconnections can either enhance or change the structure, change the dynamic of this pressure system, and that in turn will be reflected in the changing in the climate. So this is really sort of my focus, is looking at the Amundsen sea low and then sort of taking this out a little bit. So I just want to show this, and hopefully this is coming through as the video. This is just a really good kind of recap of when we think about ice cores, it's sort of understanding that everything that we see within an ice core has come from somewhere else. And I love this NASA, it's a false color image, but really showing how this kind of, the different swells, we've got the sea salts and we've got these marine aerosols that are whizzing around. We've also got some of the terrestrial records and evidence of biomass, but these are all coming from somewhere further afield. And these are coming from these land masses towards the mid-latitudes. And this is why hopefully it sort of helps to explain why the information that we can then extract from an ice core, because it has traveled from quite long distances, that is why we can look at these longer range and larger atmospheric circulation patterns. So just showing you on here, this is then we sort of see this seasonal cycle. But then one of the really important things, and I guess what I've been working most of my career on, is actually looking at the snow accumulation. So this is looking between these different seasonal markers in the ice core to see how much snow fell each year, and then using that to go back in time and see how snowfall or surface mass balance has changed. So again, I like these little videos just to show it, but now taking a slightly different view. And this one is just focusing on just the moisture in the atmosphere. And just showing you down here, so the star is actually an ice core site that I've worked on quite a lot, which is the Foligno ice core from coastal Ellsworth Land. And you can see here how the moisture is coming straight down from the tropical Pacific here, and it's directly impacting this site. So we can look at this from the other direction, as we have done, and looking from the ice cores, looking as backward trajectories, and we can see all these air masses are dominantly coming in from this Pacific sector. And particularly when we've got really high snow accumulation events, a lot of snowfall coming in, that's when these air masses are really very much focused into this small sector of the Pacific. So we can see that clearly this is going to be, ice cores from around this region are going to be really fantastic as archives, as proxies for looking back at this teleconnection over the longer time periods. So the figure that I'm just showing you here is, I'm actually going to start off looking at temperature. So when I put temperature, what I'm actually talking about for the ice core people, this is the stable water isotopes, which is a commonly used proxy for past surface temperature. However, most people I'm sure already know that it's actually quite a complex relationship. So it can be telling us about changes in circulation, changes in sea ice, and actually the fractionation processes arriving at the site. And so what we're doing here, so I'm just showing you in the bottom plot, we've got the deuterium. So this is the stable water isotope record from this Foligno ice core. And this was drilled, and it goes there and dated, goes back to 1703. So it captures a really lovely sort of 300-year record of climate variability. So we're looking here just at the isotope variability. And the record so shown here in the blue from the ice core, you can see that actually we don't see, although we get this sort of characteristic warming since about the 1950s, if we extend that record further back in time, when we go back to 1700, we see that we've actually seen very similar multi-decadal, almost 50-year sort of cycles of variability. And in fact, we've seen more abrupt 50-year warming trends further back in the record. So what we're seeing, if we were just looking at this isotope record, is that actually the recent period isn't so unusual, at least as we see it in the ice core isotope record. And this is reflected at Waste Divide and other sites across West Antarctica as well. But what's interesting is that I've then compared this record with a coral record from the tropical Pacific, so from Muratonga. And this coral record is reflecting changes in sea surface temperature. And it was just interesting to compare two very, I suppose in some ways, very similar proxy records, but from very different regions. But what we clearly see is actually there's, over this whole 300-year period, there's actually a very strong correlation between these two records. And in that we can see very clearly, particularly we've got periods of what we would interpret as cooling events and warming, and we've got the same sort of multi-decadal variability. And if we look into this in the spatial plots now, start looking at actually what was happening with changes in the surface temperature and looking at the changes in the pressure, we get these sort of similar teleconnections that we've already sort of had a fantastic review of. But just to show you, so the top two plots, so we've got the correlation of the ice core isotope record with the geopotential heights on the top left, and then with sea surface temperatures. And just to sort of show you, so the star is showing where my pointer's working, star is showing where the ice core is, and actually this little box here, and this inside this little dot, this is the coral record. So you can see we're quite far apart. And actually it's because this record here, so we see that the ice core stable water isotopes have this nice correlation, but with this sort of strange and slightly unexpected region of the Pacific, but it's within this tropical convergence zone in here. And this is why we have, as we got this lovely explanation earlier from Kyle as well, it's this region that then can propagate down and affect what's happening in the climate of West Antarctica. And again, you can see this in the pressures here. We've got this sort of fantastic connection down here with high pressure anomalies. So this was a kind of first sort of introduction for me in looking at actually these sites as their potential to explore the tropical teleconnections further back in time. But what I want to do now is move on to the snow accumulation record, because in many ways, the snow accumulation, particularly from the whole region around the Antarctic Peninsula and West Antarctica, is really interesting. And this is where we have seen much more dramatic changes. So the isotopes, as I showed you, it doesn't really, the recent period doesn't really stand out as a period of exceptional variability. However, when we start looking at the snow accumulation, we start to see that actually this recent period is arguably exceptional in terms of the last 300 years at least. And so what we have now is lots of different records that we built up. So again, I'm really just focusing on this Foligno ice core, but also looking at different ice cores from very close by sites. And we see that this is very reflected that during the 20th century, we get this very abrupt increase in snowfall, and that actually the snowfall during the recent part of the record is outside of anything we've seen over the past 300 years. Here I'm just focusing in from 1850. But again, what I want to show is how this is related to changes in sea surface temperature, but actually sea surface temperatures this time in the Western Pacific. So putting here again to then look more at the spatial correlations for this record. So this is the isotopes correlated with the sea surface temperature reconstructions. But I'm showing it 2 different time periods, because if we look at what's been going on just in the instrumental period, we see this very strong, so this is on the left, or plot A, we see this very strong kind of ENSO-like pattern, or an IPO pattern, where we've got a strong correlation between warm SSTs in the Western Pacific and then cooler SSTs in more the sort of tropical and equatorial Pacific. So we'd be tempted to look at this and think this is telling us something about, ENSO and how we could use this to interpret this further back in time. But looking at the models, taking this back further, so taking this back to 1850, we actually see that this pattern becomes diminished. Now, I know there's a lot of caveats to put in here as to, how accurate the models are, and particularly across that whole region of the equatorial Pacific is very difficult. We have very little data within there to look over the longer timescales. But essentially what we see is that the pattern is diminished, but actually this relationship with sea surface temperatures over the Western Pacific seems to be maintained over the longer time period. And so on the bottom plot here, we've got the snowfall is in the blue, and then the sea surface temperatures just extracted from that black box that I've just sort of highlighted up here in the Western Pacific. And what we can see is that actually the sea surface temperatures here seem to display very similar trends. So we've got this very clear increasing trend in sea surface temperatures and snowfall during the 20th century, and very similar kind of multi-decadal variability as well. But what I want to kind of then move on to is highlight, so the temptation with that is that then you think, okay, we've got a clear tropical teleconnection, let's take this back in time, or could we use this to reconstruct the teleconnections and produce reconstructions? But actually, I think what's important to look at is that when we take these records further back, if we're just looking at indices of tropical teleconnections, the temptation would be to look at the SOI, or maybe looking at just the SAM, is that we actually see that this relationship isn't stable through time. So on this plot here, I'm just showing you, so just to begin with here, we've got the spatial correlation plot. Just to remind you, this is the snow accumulation and how it has this really, really strong relationship with sea level pressure and the Amundsen Sea. So this is the Amundsen Sea low. So when we've got very low pressures, we have lots of snowfall. And this is because the low pressure system pulls down sort of warm, moist air from the tropics. And that results in increased snowfall and warmer temperatures on the peninsula. And so again, showing you then just the normalized snow accumulation record here in the black, and comparing it, this is the sea level pressure. So this is what we would be looking at, the sea level pressure changes. So we can see they're related quite nicely. But then if we start to look, so now looking just at the bottom plot, if we start to do some correlations, and these are running decadal correlations with these climate indices. So first of all, with the SOI, or looking at these changes with the SAM, it's a little bit messy to see in here, but essentially the takeaway message is that there isn't a clear and consistent correlation through time. What we see is we've got periods where we've got very strong positive correlations, but also periods where we've got very strong negative correlations that are significant as well. So this really tells us that this relationship is not stationary. So there's obviously changes in variability. And there's been some fantastic work looking at this particularly, and how this might then explain why we see such big changes in things like snowfall and temperature and winds that we've seen during the period since the 1980s and particularly into the 90s. When we seem to have this sort of perfect storm, if you like, where the modes of variability, particularly the SAM and ENSO, are working together. So they're working in phase to really enhance this tropical teleconnection. And that's why we see these very big changes, particularly. And so it's this sort of interplay between the different modes of variability that's been really important, and potentially explains why we see such dramatic changes during the latter part of the 20th and into the 21st century that we didn't see or didn't experience during the previous sort of couple of hundred years. So taking this on further, we've built on a range now. We've got a whole collection of ice core records. So a big compilation of 80 ice core snow accumulation records that allows us to actually look at this, not just at an individual or just a small region, but actually expanding this out. So this is some work from Yetan Wang, focusing on the ice cores that we've got, the snow accumulation records from across West Antarctica, breaking this down into different sectors. But essentially it's showing the same kind of finding, is that yes, there's a strong influence of the Southern Annular Mode and ENSO on the snow accumulation, particularly in the Antarctic Peninsula and West Antarctica. But when we take this back further in time, we see that this relationship isn't stable. So there isn't a consistent pattern through time. It appears to be something that varies, and it's particularly relating again to this interplay between SAM, ENSO, and particularly the PDO, which we're showing down here, which we saw earlier. So we've got this kind of, particularly negative PDO during the 50s, and then a more positive during that before we get to the 80s. So this is where we're really building on work, and I think one of the key things to say is that when we're looking at ice cores, they're fantastic as an archive, and they're fantastic looking at the individual record. But actually, the power of the ice cores is when we start to bring all this data together and look at what's happening across multiple sites, because this allows us to produce more robust reconstructions, really taking out some of the artifacts of maybe local noise and looking at these bigger changes. So this is just in my final part, I want to really make a bit of a plug for future work, really. And this is why we had the data call as part of the CLIVASH 2K working group to try and pull together what other information can we get from ice cores. So we've looked at snow accumulation, we've looked at stable water isotopes. And arguably the stable water isotopes may not be the ideal one to be looking at these tropical teleconnections, but clearly we're seeing something very interesting with the snow accumulation. But actually, is there something else we could be looking at, something better? And so the data that we've been collecting is the sodium and sulfate records from all ice cores that were made available to us. And we had 117 records submitted, which is really fantastic, from across Antarctica. And actually, so the plot just showing you here is all the different ice cores that have been submitted. And the color coding, I'm afraid it might be a bit faint, is showing you the different time spans. So the longest records that we have go back 2,000 years. But obviously a lot of the records, particularly around the coast, are much shorter, focusing on the last few hundred years. But that's still providing a fantastic archive of way more records than we thought, and actually across the whole range of Antarctica. So we've got, from the high elevation sites to the coastal sites, which is really good. And the reason that these, I think, are going to be fantastic or have potential for looking at these tropical teleconnections is because, particularly for sodium, we're seeing that there's really strong relationship with sea ice over interannual scales, but actually over interdecadal scales as well. And we know that sea ice, as we've heard before, is strongly influenced by these tropical teleconnections. And the other key parameter here is winds. So sodium is particularly, it's arriving at the ice core sites because it's being driven by winds that are uplifting this from the ocean and transporting it. So again, we've got potential here in that we've got multiple ice core sites that can be used to reconstruct winds and sea ice around Antarctica, importantly, in nearly all of the sectors and all of these different basins. And so this, I think, is where we hopefully will be able to start looking at the longer term, how these tropical teleconnections have either maintained or varied through time, but actually taking a more sort of hemispheric view on this, which I think is really promising. So that was my kind of just very quick insight into what ice cores can do, and I really just sort of wanted it to trigger a bit of discussion, really. But we see this strong influence, particularly for the West Antarctic ice cores, of this tropical Pacific teleconnection that's particularly strong during the instrumental periods. But the fantastic advantage of the ice cores is it allows us to take a sneak peek into what was happening before the instrumental period. Admittedly, we have less data, less certainty, but we can actually then extend this relationship over centennial timescales. And what this has shown is that in many cases, there is evidence that this tropical teleconnection has been maintained. So the fact that we can compare an ice core from West Antarctica and a coral record from the tropical Pacific over 300 years and see such a remarkable relationship shows that there's clearly some element of this tropical teleconnection is maintained over the multidecadal timescale. But what's important, I think, to also remember is that actually it's the relationship between these different climate indices. that appears to be quite important. And there's also regions that are not associated with the traditional teleconnections, so particularly looking at things in the Western Pacific. And looking at these relationships with just the indices shows that actually they're not stable through time. So we have evidence that this recent period may be quite unusual in that we've got such a strong teleconnection with the Pacific, but actually if we look further back in time, some of these relationships and these correlations with particularly the SOI or the IPO may break down with time. And just finally, to sort of more of a plug for future work really, is that actually now we need to start using the ice cores in different ways and start extracting more information from them that could be beneficial in exploring these teleconnections over the longer time periods, but also over the whole of the Southern Hemisphere. So we can really start to look at the interplay between these different basins over the longer time scales. And with that, I will finish. Thank you.
Thank you so much, Liz, for that excellent perspective on longer, possibilities of connectivity between the tropics and the poles. Everything is not as straightforward as we see in the modern times. As we look in the past, we find a lot of complications. So thank you so much for that. We don't have any question as of now, but I think we keep getting it as sometime. I think, of course, please be ready for it. We as of now move forward to the final speaker of the day, Dr. R. Krishnan, who is the director of the Indian Institute of Tropical Meteorology, Pune, who has been actively involved with the IPCC reporting, as well as he's also a member of the Joint Scientific Committee on WCRP. We look forward to him actually listening what exactly happens closer to the tropics, especially the third pole, and how this climate change affecting that particular regions. Over to you, Dr. Krishnan. Yeah, thank you so much.
Yes. Thank you, Dr. Thamban. So are my slides visible?
Yes, can you make them again view as right?
Yeah, view
Full screen.
Full screen mode.
full screen. Okay, great. Yeah,
Thank you.
yeah. Thanks a lot, Dr. Thamban and the SCAR organizers for this opportunity. We heard three interesting talks on the teleconnections between the tropics and the Antarctica. So now I'm slightly shifting the gear. We are going to the third pole environment, that is basically the Himalayan region. And let's take a look at how climate change has been affecting some of the precipitation extremes in this region. And also I will touch upon some of the teleconnection aspects that are relevant to the precipitation extremes in this region. So this is the latest state of the art, state of the global climate from 2021. So the means, the temperatures, the global mean temperature in 2021 was 1.11 degree above the 1850 to 1900 average. And if we see the more recent 7 years, that is 2015 to 21, they were all the warmest years on record. In fact, 2021 was less warm because of the influence of a moderate La Nina during the start and end of the year. And the global mean sea level has reached a new record in 2021, rising an average of 4.5 millimeters per year over the period 2013 to 2021. And we are seeing exceptional, very exceptional melt in the Greenland during the mid-August 2021. And in fact, there was a summit station in Greenland which experienced rainfall, this is an altitude of about 3,216 meters. The Greenland ice sheet, so we are seeing rainfall in those places, and exceptional heat waves in different parts of the world, North America, Mediterranean, so on, and also parts of Europe. So the climate change is a reality. And now the IPCC report, these are some very powerful messages that came out from the 6th assessment report, that human influence has warmed the atmosphere, ocean, and land. And the changes are widespread and rapid, not just in the atmosphere, also in the ocean and cryosphere, which we saw in some of the presentations. And the Antarctic has also been experiencing decreases in the sea ice. And climate change is affecting many weather and climate extremes in every region across the globe. So this is an important point. Weather and climate extremes are also altering. there is a strong evidence of observed changes in extremes such as heat waves, heavy precipitation, droughts, and tropical cyclones. And in particular, their attribution to human influence. This has come out very clearly in the 6th assessment report. And continued global warming is projected to further intensify the global water cycle, including its variability and global monsoon precipitation, as well as the severity of the wet and dry events. These are some points I just wanted to touch upon. So one of the important consequences of the global warming is the increase in the atmospheric water vapor, basically due to the temperature dependence of the saturation water vapor, of the saturation vapor pressure. So with increases in the temperature by every 1 degree, the water vapor in the atmosphere can increase by 6 to 10%. And this is a direct consequence of global warming. And one of the important consequences is that the frequency of heavy precipitation events is also expected to increase at the same rate, about 7% per degree warming. And we are already seeing that this on a global scale, when we are seeing that hot temperature extremes over land, they are increasing. So what used to happen once in the pre-industrial period is now happening, is more likely to occur at 2.8 times more frequent. And with higher degrees of warming, 1.52 degrees, the frequency is going to increase, as well as the intensity of the heavy hot temperature extremes. Likewise, the heavy precipitation over land also is projected to increase with every additional warming. And what was happening once in the pre-industrial time is now happening about 1.3 times more frequently. And also the intensity has increased. And with further warming levels, the heavy precipitation over land is projected to increase. But this is on a global scale. Now, why is it relevant to now? We are looking at the Himalayan region. Why Himalayas is very crucial is because this is one of the drivers of the strongest monsoons on the globe. And this is a source of 10 major Asian rivers. And it is the largest reserve of ice outside the polar regions. Also, it's a biodiversity hotspot, and it has a diversity in culture, traditions, and languages. And Himalayas has also been experiencing rapid warming. And this is a picture from our National Climate Change Assessment report from the Ministry of Earth Sciences. So the rate at which the temperatures in the Hindu Kush Himalaya have increased, they have warmed at a much faster rate as compared to the temperature increase over India itself. So this is an important point. So the Himalayas have been warming at a very fast rate. And the other aspect is that the higher elevations, when you go, the rate of warming is happening at a much faster rate at the higher elevations. And this is known as the elevation dependent warming. So typically about high elevations more than 2,000 or 4,000 meters in this region, especially the Tibetan Plateau, the rate of warming is almost something like 0.5 degrees per decade, as compared to the low elevations where the warming is much slower, something like 0.2 degrees per decade. So this elevation dependent warming is still a topic of research, and why it's happening. But this is seen in the observations. And because of this increased warming in the third pole environment, it has, this is from the special report of the AR6, the Ocean and Cryosphere Special Report, SROC. So the glacier, snow, and permafrost has declined and altered the frequency, magnitude, and location of most natural hazards such as landslides, avalanches, and flooding. And however, it has major impacts on the water availability. So the water availability has been affected by climate change. This attribution comes with a kind of a high confidence. Although when we look at flood or landslide or avalanches, their attribution has a kind of low confidence that we have to keep in mind. And so climate change is already affecting this region, especially in terms of the water resources. So this particular talk, I will give some examples of heavy precipitation events over the third pole environment during the summer monsoon season. And the main issue is the event attribution. When we some of these examples which I will be touching upon, like the heavy rainfall during June 2013 in the Northwest Himalayas, which led to major flooding in Uttarakhand. And we also, although we understand the dynamics of these events, why it happened, what is the role of climate change? So this event attribution has been a very, very difficult, challenging scientific problem. Likewise, we had very heavy rainfall in the Leh Ladakh region. This was during July, August 2010. And it's basically a kind of dry desert area, but it resulted in very heavy precipitation, flooding. It led to flash floods. So let us look at that particular aspect. And also, we have also flooding in the southern slopes of the Northeast Himalayas. Typically, it happens during when we have a weak monsoon, or what we call is a break in the Indian monsoon. So the plains of India receive less rainfall, but we get a very heavy rainfall in the foothills of the Himalayas, in the Northeast Himalayas. And then this happened in this beginning of this year as well. And so let us try to understand some of these heavy precipitation events during the summer monsoon season. Basically, this picture shows that the Indian summer monsoon precipitation processes, it involves multi-scale interactions. You have the large-scale monsoon also which has you have a strong flow from the high pressure to the low pressure. So this is what this is what drives the large-scale monsoon system. Within this monsoon, you have this low on the subseasonal time scale. We have the active and break spells, the movement of the rain bands from the equator to the pole. And also on the shorter time scale, we have the synoptic systems, the low pressure systems, which form in the Bay of Bengal, move westward into the Indian region, and they can produce substantial amount of rainfall. And we also have the metropospheric cyclones over Gujarat. So basically, all these synoptic systems and the intraseasonal variability, they're all associated with organized convection that happens during the summer monsoon season. So there are basically, the main point is there are multiple scales that are all interacting. And the question is, if you want to do the event attribution, what is the role of climate change on a particular event? It becomes a really challenging problem. And so let me just talk. This is the example of the 2013 heavy precipitation over Uttarakhand, and this had a very strong teleconnection to the polar region. I'll be coming to that. Many stations in the Western Himalayas. This was during something around 16th of June, when this heavy rainfall happened in Uttarakhand, and several stations received more than 200-300 millimeters of rain in a day. And this is just showing the statue, a mighty Shiva statue. It was almost, it was very badly affected because of the flooding. We analyzed, this was a study by my colleague Vellur et al., in which we analyzed 34 similar cases of heavy precipitation in the region, in the Northwest Himalayas. And what the common pattern that we find is that there is the monsoon was very, very intense. This is what we call as the Tibetan anticyclone. So this is a typical feature associated with the monsoon convection. When the convection is very strong, the anticyclone develops in the upper troposphere, basically the upper troposphere and the lower stratosphere. It became highly unstable. So this was 16 June 2013. The Tibetan anticyclone was very, very active. It was very unstable. And around the same time, there was a low pressure system moving from the Bay of Bengal very quickly to the Himalayan region. And same time, it also coincided with a very deep mid-latitude trough. It is almost coming from the polar regions. So there was this convergence of the mid-latitude trough and the low pressure systems from the Bay of Bengal, which carried the moisture from the oceanic regions and led to very strong convergence in the Himalayas. And so this is a very, very important case of interaction between the tropical and the extratropical circulation, which resulted in heavy precipitation and flooding during 2013 in the Himalayas. And this we also see this in the satellite pictures and the reanalysis data. You can see the low pressure. This is on 13 June. This is on 15 June. This is a paper by Bob Hose et al. And on 17 June, you can see this very deep trough as well as interacting with this low pressure system. and substantial amount of water vapor being transported from the bay and also from the Arabian Sea into the Himalayan region. So the point I'm trying to drive is the water vapor is a very important component to trigger this heavy precipitation. And with climate change, as we are going with every degree of warming, the water vapor in the atmosphere is going to precipitable water will increase by 7%. So the consequences of this heavy precipitation is going to become more severe in future. And so the next point is that this is the Leh flash floods. Leh is basically located in a very dry environment in the Ladakh region of Jammu and Kashmir state. And it's basically a high altitude cold desert. And so during end of July and August 2010, just immediately after the flooding in the Pakistan and the upper Indus Basin, heavy rainfall, this region received torrential rains and led to flash flooding. And this study basically what they noted was this was the time when convective cells formed in the Tibetan plateau. And they propagated westward. So there is a very strong diurnal variation in the convection. So during the daytime, as the plateau gets heated up, these convective cells formed in the Tibetan plateau, and these mesoscale convective systems, they propagated westward. Around the same time, you had the moisture influx from the Bay of Bengal. And so this moisture actually acted as a fuel and led to this very deep convection and flash floods and heavy rainfall and flash floods. And this is the picture of how this moisture is being transported. You can see on a synoptic scale from 3rd August to 4th August and 5th August. And around the same time, you have a lot of convective activity from in the Tibetan plateau and these mesoscale convective systems moving westward. So the interaction between the water vapor and the convective systems can lead to these heavy precipitation events. And the third example I will talk about is this in the northeast Himalaya and in the northeast slopes of the foothills of the Himalayas. Whenever we have a deficit monsoon over India, when the monsoon is weak over the plains of India, what we call as the break in the Indian monsoon, the foothills actually receives a substantial amount of rain. And this happens when the water vapor is channelized from the Bay of Bengal towards the foothills. And at this time, the monsoon trough is also, the low pressure trough is also situated near the foothills. So, and there is an interaction with the subtropical westerlies, which are much more, they intrude southward during this period. And you can get heavy rainfall and flooding. And we see such reports and these rhinoceros and other animals in the northeast. So they are very badly affected, and it leads to major flooding in the Brahmaputra region and inundation. And of course, there are flood inundation maps that are being produced for the Brahmaputra and the Barak rivers. So the problem is, so with climate change, how these extreme events, specific, which are highly dependent on the circulation changes, how do they change? So this was a study where we used a very high resolution model, something at a 35 kilometers grid scale, and we had a natural experiment, and where the model was driven only by natural forcings like the volcanoes and solar irradiance changes. And then we had a historical experiment where we changed the greenhouse gases, the aerosols, land use, land cover change. And what we find is when we compare the mean, this is 1950 to 2005, we take the difference in the climatological mean, precipitation, and circulation. So the historical experiment actually showed a weakening of the monsoon. Despite the increase in the greenhouse gases, the other drivers like the aerosols and the land use changes, they tend to weaken the monsoon flow, and we get a deficit in the rainfall over India, whereas we do see increase in precipitation over the foothills. And this attribution also showed that the weakening of the monsoon and the increase in the precipitation over the Himalayan foothills, what we see during the breaks, is because of mainly the anthropogenic northern hemispheric aerosol emissions. If we had only greenhouse gas emissions, we would find an intensification of the monsoon and intensified precipitation. So this is just I wanted to mention. The other point is that there could be remote drivers, like because the Arctic sea ice is declining at a very fast rate. And in the coming few decades, practically Arctic could be ice-free. And this is mainly coming because of the human activities. This is again from the 6th assessment report. The future projections of the Arctic sea ice show a major decreases in the future as the climate is warming. One of the consequences is it could alter some of the teleconnections with the mid-latitudes and the tropics. And typically when we have when we have changes in when we have a very cold polar air and we have a very confined vortex in the polar vortex, and the jet stream is usually very strong. And so once we weaken the ice, when the ice reduces in the polar region, basically the meridional temperature gradients between the mid-latitude and the poles can weaken. And so the polar jet stream will become weakened and it starts meandering. And these meanders in the jet stream can affect extremes in the temperatures as well as precipitation in the mid-latitudes. And for example, it can lead to extremes. For example, during 2010, we had the Russian heat wave. It was associated with variations in the jet stream. And this time there was also due to the Arctic amplification, strong warming in the polar Arctic region, also due to the decrease of the Arctic sea ice, the albedo actually decreases. And due to the decrease in the albedo, the warming is further amplified due to absorption of the radiation. And this in terms of, so the temperature, there's a positive feedbacks, the warming increases, and then due to the meanders in the jet stream, they can affect extremes, temperature extremes in the mid-latitude. And also some studies have discussed that they can also influence precipitation extremes in the subtropical areas. And so the important point is changes in the Arctic sea ice can have implications on the circulation changes and extremes over the mid-latitudes and tropics. And in fact, one of the recent study from NCPOR, Saurav Chatterjee et al., they showed that decreases in the Arctic sea ice, especially in the Kara Sea, can influence large-scale teleconnection patterns and lead to extremes in the September, during the month of September, extreme rainfall over the Indian region, and they describe some of these teleconnection patterns. So in summary, I just want to conclude that heavy precipitation in the Hindu Kush, Himalaya and third pole, this involves a lot of atmospheric dynamics, which are linked to the monsoon circulation, the Tibetan anticyclone, also interactions with the extratropics and the polar regions. And you also have clouds and convection, how the mesoscale convective systems are organizing, the latent heating and moisture transport, and also large-scale SST gradients in the Indo-Pacific can also alter these heavy precipitation events. And we also described some of the examples of the Uttarakhand 2013 event, the Leif event in 2010, and also Northeast India heavy precipitation events. So one of the important requirements is we need event attribution studies. Specific events can be attributed to climate change. What is the role of internal variability? What is the role of teleconnections? We have to quantify them. So this will need large ensemble simulations to bring out the signal to noise ratio. And so the climate change can impact a heavy extreme precipitation mainly through increases in the water vapor. It can also lead to intensification of the deep convective events over the tropics, monsoon and third pole environment, and intensified moisture transport into the precipitation region. This was also brought out in the earlier talks. So moisture transport is going to intensify into the precipitation regions. And there could be remote drivers like the Tibetan plateau warming, the declining Arctic sea ice, large-scale circulation anomalies, and increased snow and glacier melt over the Himalayas. So clearly there's a need to improve the prediction potential of the heavy precipitation events in the third pole environment, which means we need to really enhance our early warning systems and also link research to operations and applications. So with this, I would like to come to the end of my talk. Thank you very much.
Yeah, thank you, Dr. Krishnan, for that wonderful and interesting take on third pole, how it's getting affected by the extratropical as well as polar systems, as well as how it's complex the system it is. We don't have any immediate question to you, but I think as we are moving on to the panel discussion and question and answer session, I think I expect there could be more questions coming in.
Okay, thank you.
However, I would like to talk to, I think there's one question to Kyle Clem, which could not be taken up at that time. So maybe as we proceed to the discussion, I would first start with a question to you from Babula Jena to Kyle. Essentially was just looking forward to understand how does the atmospheric rivers actually influence the actual thermal structure, ocean thermal structure. He's basically talking about how do these atmospheric rivers have an influence at all on the ocean thermal structure. Maybe both Sichan as well as Kyle should be able to have some view on that.
I don't. Oh, hopefully you do, Zishan.
Yeah, so
I don't know.
Okay, so it's a little bit complicated. It depends on the location of the circulation. So usually the change of the circulation, like the emergency low, can change the economic pumping around the West Antarctica, and it can change the direction of the warm water intrusion. But it's very depends on the location of the circulation. So the anomalous circulations, like is if is to the offshore area, so it is possible that there will be a, let me see, easterly wind along the coast. But if it's more inland, it could be a westerly wind close to the coast. So it's possible that even if we just intensify the MCC low, if the location are the anomalous circulation center are at different location, we may have opposite effect of the subsurface ocean circulation. That's one aspect. That's one effect. The other effect is that if the atmospheric circulation can drive sea ice, it can, by both it can help to form or melt more sea ice. Meanwhile, it can transport sea ice to like a lower latitude. This process can change a lot. Like it can change the stratification of the ocean. It also sometimes can also heat the subsurface ocean. I think two aspects, but both quantified. Yeah, not both qualification.
In fact, there's one more question to all three of you polar people. Basically, we all talk about the tropics influencing the polar regions. You are, or as well as to the Dr. Krishna. In fact, what is your view on Antarctica itself affecting tropical climate? This is from Dr. Manish Tiwari. This question. Is Antarctica affecting the tropics, especially some large systems like monsoons? Is there any evidence to it?
Yeah. So there are like many recent publications show that Antarctica may contribute to the tropics. I think one is from England and the Clare Desert in 2019 or 18. I forgot. It's in Nature Climate Change. I remember. So it's said that if we melt the sea ice in the future around Antarctica, we might intensify the ENSO in the tropics. That's just future projection. There are also many recent publications about how Antarctic sea ice, like the sea ice dipole around the West Antarctica, it may impact on the East Asian monsoon, and it may impact on the summer precipitation over South China, and a lot of related papers recently. Yeah.
Right.
Yeah.
Kyle?
Yeah. It comes.
If I can just add to what Shizan said. Yeah, I fully agree. So the impact of the Antarctic ice melt on the monsoon, I think it's not a very simple problem, because it is going to affect the circulation patterns in the extratropics and subtropics, and maybe also some of the teleconnections like the ENSO modes of variability can be altered, and so it may not be a very straightforward problem. And so if you are making any changes in the, for example, the subtropical high, the mascarene high, and those areas which are really in the subtropics, they are going to, through the circulation changes, because they are going to channelize the flow from the southern hemisphere to the Indian monsoon. So it can have a consequence, but bringing out that signal is not going to be easy. You need large ensembles because of so much of internal variability. That problem may not be that easy to demonstrate. Likewise, I suspect the same because there were very nice talks about the role of tropics, the tropical convection, how it is affecting the sea ice in the Antarctica, and also snow accumulation, which I saw from Lee's talk, how the moisture being transported from the tropics, how it's influencing the increases in snow cover. And so how good are models in capturing these type of teleconnections? Because tropical convection itself is a challenging issue. And you have these different tropical waves which are propagating. So how is the evolution of these waves going to change in the changing climate? That is not known. The propagation, because you have the phase, you have the amplitude, how these waves are going to, and there are different waves. So it's not going to be a very simple issue.
Yeah.
Kyle, would you like to add something to it? You're muted.
No, I'm okay. Thank you.
Would you like to add?
Well, I was, no, not really. I was just going to echo what Zishan said. So when we talk about how the poles, Antarctica influence the lower latitudes, it does appear like it largely comes down to the ocean. And so in that case, it largely comes down to changes in precipitation and sea ice and changing the formation of dense bottom water and changing the thermohaline circulation, which can have feedbacks in the tropical areas, which is poorly understood because we can't really observe it. We have to rely on simulations that are not constrained by a long-term record. And so it's an interesting question, and then there will be feedbacks within it. So, but Zishan did a good job explaining.
Thank you, Kyle.
Yeah, so I think I also heard from Meloth that you are with the long term, these things are quite unstable. They're not stable through time. So what is your take actually? So as you move forward in time in a rapidly changing kind of climate system, actually, what do you think actually is? Do you have any what do you call the statement? How it's going to be, these relationships going to work?
Well, I was actually going to finish off on the previous point of saying, because one of the advantages, as you know, Thamban with the ice cores is that we can kind of look back at the much longer time scales. And so the sort of teleconnection between the tropics and the poles, or thinking of it the other way around, and the poles to the tropics, these are the longer time scale climate changes that we've seen over sort of multi-millennial time scales, and how we see changes. Normally we're focused on the changes in the sort of North Atlantic and the polar regions, and how that reflects through the oceanic circulation. But again, obviously for Antarctica, particularly around the sort of Weddell Sea, plays a really important role in that kind of interplay with the tropics and altering the oceanic circulation. So I guess that was just, I was going to finish off and just kind of say that that's one of the important things. So particularly looking at these large scale, changes during the glacial period, downscaled Erskine events, where you sort of see these flips in the temperature. That's very much a kind of, is it the tropics triggering the ocean, the Antarctica, or Antarctica triggering the tropics? So that was all I was going to kind of bring into that. But I think then Thamban asked me the question of what's going to happen the kind of moving forward. That's even harder to answer. But I think that it's really important, and it's really, I think one of the key things with this is it's really important that we bring together the different kind of time perspectives. So, we've got the experts here in sort of Carl and Zishan looking at the very modern processes, but over very short interannual, interdecadal timescales. But it is important that we then kind of broaden that out and start to look and see whether, the interplay between these over the long timescales, because we could be, misled in looking at, just because at the moment we're in this sort of strange scenario where we have everything kind of working very much together. This may be an unusual phase that may change, or it could be that we've actually, this could be where we're at moving forward. But I think we really need that longer perspective. And one of the questions, which unfortunately I answered in the chat by pressing the wrong button, but it was looking at, how long do we need to go back? And one of the focus of the sort of Clivash project is looking at trying to get reconstructions back 2,000 years. Because if we really want to be looking at these interdecadal and intercentennial, you need those longer records. And about 2,000 years seems to be about the right timescale to add that sort of, on a very simplistic point of view, the baseline, natural variability, and then really understand what's been happening on the more recent sort of anthropogenic kind of period that we're in. So that was all I was going to add to that, but I'm sure the others have got more.
Yeah. Shichen,
I
do
have
you
a
want to
question.
add to something on that?
No, I think I really agree with Liz. So, so yeah. So maybe not more too much. Yeah.
I have a question for Liz.
Yeah, me too.
So, how do
Right.
you, how are we able to use past variability to understand what's going to happen in the future in unprecedented times with such rapid changes of all aspects of the climate system that we haven't seen in the past?
I think often when I think about this, it's trying to understand. So, you know, a lot of when we're looking for the future, obviously, we're not going to be using the paleo records to do that. But what we do is we need the models. And I think the key thing that the paleo data it can do is provide the better baseline, the better inputs, you know, baseline data for the models to be able to make those predictions. Because I think there's been some fantastic work looking at the different CMIT 5 and 6 models and showing that, you know, the different initial input that you put into that can have a huge effect on what your output, particularly looking at things like sea ice. So I think the bit that I'm saying that the ice cores and the sort of longer paleo records can do is they can make sure that we are much more accurate in our initial conditions. And then that will ultimately kind of help the models to be better at their job of predicting what's going to happen next, hopefully.
Thank you.
I have one question to Liz. Yeah, I really like that snow accumulation picture which you showed in the Western Antarctica. So, so has it been increasing the snow accumulation? Because I saw that it is since the 1930s there is a substantial increase.
Yeah. So this is some work we've been doing for quite a few years. So initially, just looking at the ice cores from the peninsula, we saw this, you know, very dramatic increase. And then building that up. So a few years ago, we got a compilation of nearly 80 ice cores and looked across the whole of Antarctica. And we're able to convert that then into total surface mass balance. And actually, during the 20th century, particularly, this big increase in snowfall is quite consistent pattern across East Antarctica as well. So it's quite a consistent increase. And, you know, some of the findings we did with Britt Medley were then showing that actually it's enough to have mitigated sea levels during the 20th century. So it's a significant enough change that we need to be, you know, taking this into account in particularly our future predictions, that actually changes in snowfall, are important.
So this data is latest is until when it is.
Most of the ice cores. So unfortunately, we do have a little bit of a top end issue. In that a lot of the ice cores from Antarctica were drilled around the 1990s. So some of the records don't extend too far into the recent time, but we have quite a few, you know, we've had some really great sort of campaigns. So we've got records that extend into sort of, you know, early 2000s. And that's kind of the top end of our records. And then one of the restrictions that we do have with a lot of, you know, most of the changes that we're seeing are happening around the coast, where we get a lot of snowfall. So unfortunately, that means we don't have a lot of very long records. So we can really focus on like the 20th century really well. But if we try and get back to this sort of golden sort of 2000-year record, it's quite hard to do.
So maybe I have
Thank you.
Sorry. I have just one comment about the future projection. That recently we find that the phase of IPO and AMO after 2015 they are changing right now. So we expect some like a different signal of both surface air temperature and the sea ice. Actually, Kyle and I and several other professors we are working on this work is like we try to figure out what will happen or what is happening right now. Like the East Antarctic becomes warmer and the West Antarctic Peninsula, the warming trend is slowed down. And actually, I have another question to Liz. So this question it puzzled me for a while since the teleconnection pattern is usually has some very strong seasonal feature, but the paleoclimate record, like the ice core, usually the temporal resolution is just annually or like it's longer than a year. So I really want to ask whether there's some way or some first, can we see this kind of signal, and whether we have some way to maybe retrieve some seasonal signal from the ice core data.
Yeah, that's really interesting, and that's where I say, you know, how important it is that we work together with the, you know, you guys are looking at very much at the seasonal changes and much shorter timescales, whereas with the ice core, the dating generally is exceptionally good, but we are normally referring to annual averages. So we're talking about what's happened throughout the year. Whereas we know, unfortunately, snow doesn't fall equal amounts throughout the year. If it did, we could just segment it up and give you a seasonal record, but that doesn't work, unfortunately. So that is something that we need to take into account, is that a lot of the records will be seasonally biased. So one thing that, you know, for the cores that I particularly work on, actually the seasonal variation isn't huge. So some of the cores, it's not, but generally you get more, you know, for the Peninsula and West Antarctica region, it's more in the spring and the summer. So you get this sort of pattern. So yeah, that's something that we need to take into account, is that potentially then when we're correlating, so when I'm then correlating with annual average teleconnections, that we're missing some of those finer detail. And that's where, you know, we really need to kind of be working together with more the shorter timescales.
Okay, thank you so much.
Yeah,
Thank you. Again, I got another rather leading questions for you, some of you Antarctic guys rather. As we learn that actually there are more and more extreme precipitation events are increasing, and that, as Liz was talking about, actually we are already facing a problem. Actually, maybe just in a couple of events, you have almost 50% of the entire annual precipitation occurs in Antarctica. As we move forward, especially since you talk about this rapidly warming world, are we going to find more and more this increase in extreme events in Antarctica? Also, especially the atmospheric rivers, for example, are they going to be more severe or going to be more serious types? Questions to all of you, in fact. Anybody could start. Kyle?
Sure. So I can answer perhaps on atmospheric rivers. So when we think about extreme precipitation events in atmospheric rivers, we have to think of two things, not just the warmer atmosphere being able to hold more moisture. We assume that we're just going to get a 7% increase in precipitation with a 1 degree Celsius increase, but precipitation is dynamic. And so everything else has to fall in place as well. And so it doesn't just work that way. And so with an increase in global temperature, you have the potential for more extreme events, so long as the dynamics come together to support it. And so my comment would be, yes, that we would expect more extreme precipitation events and more intense atmospheric rivers going forward, but it's complicated because the dynamics has to come together as well, which operates to a degree independently of what's going on with global temperatures.
Well, Susan would like to add to it?
Maybe no more than
Right. So then there's a question, in fact, a general question also to guys, actually, especially the modelers. How will these teleconnections are well represented in large-scale climate models, or in CME6, for example? Are you able to pick them or not?
Yeah. No, I think this is so we have done some attribution studies. In general, the models show that the Clausius-Clapeyron relation, the increase in water vapor models, the thermodynamic effect models are able to capture. But as Kyle rightly mentioned, there is a circulation dependency, so which is what makes it difficult. And even when you are looking at seasonal anomalies in the precipitation, models are able to respond to whether you're applying a greenhouse gas or aerosols, they're able to get the contrasting signatures, but only the amplitude of variability is reduced in the models. What you see, so this, for example, the Sahel rainfall, people have studied the decadal variability of the Sahel rainfall. The models are able to, so when you make the changes in the atmospheric composition, greenhouse gases or aerosol, you are able to see the signature, but the variability is underestimated. The signal is underestimated. It is very weak in the models. That is something we have to improve. So that is going to be one of the challenges. The signal will be very weak. So you need large ensembles basically to bring out the signal. What is the effect of the climate change on a particular, especially when you are doing event attribution. We need to have large ensembles to bring out the signal, forced signal.
Yeah, thank you. Would Sichan would like to add to it?
Yeah, so a little bit more. This is like I think whether we can well represent the teleconnection pattern depends on two parts. The first is that whether we can well represent the source, like the phase of IPO and AMO. Usually, the CMAP model cannot very well represent the phase of the IPO or CMO. So that's why when we look at the teleconnection pattern, if we just do the ensemble mean, we will average all of the signals, and sometimes we get nothing. So usually most of the model can like at least qualitatively it can get a right pattern, right teleconnection pattern if we give them a right tropical signal. So like if we hit the tropical Atlantic or hit the Eastern Equatorial Pacific, we have a right pattern. That's one thing. So but most of the time we don't have a very good like a tropical signal. Yeah.
Great. So as we get closer to the our time schedule, and also there is one question for Sichan. Please look into the chat box and try to answer them because it's slightly longer question. Maybe you could answer him directly. It would be nice. Just before closing down, I just want to take one statement or one final statement actually from you guys actually that. How it's going to be do we really understand everything, or there are still gaps that in knowledge actually, or teleconnections between this polar and tropical regions, which that need to be addressed in a very emergent way actually? That's just one question to all of
I can jump in and say no. No, we still need a lot more data over the longer time periods. But also potentially if we could break this down to seasonal, that would be my kind of response to this. Yeah,
I agree. I think we need especially how these modes of variability are going to change with climate change is not well understood. At least, for example, ENSO, how ENSO is going to change in a warming world. AR5 assessment said that with warming, with future warming, you will get the El Nino-like pattern, more like El Nino-like pattern. This was in the 5th assessment report. But now recent studies are showing that it may not be so. We don't understand many of the processes in the cold pool in the Eastern Pacific, in the cold time, and especially related to the clouds. And so there are problems in the SST biases are very large. And so that's a big issue. So how these modes of variation, especially a big one like ENSO, how it is going to change is not known. So it's good. That means other modes of variability is going to be equally challenging.
Thank you.
Something like ENSO is we have challenges there, and it's a big problem.
My response is we know enough. We don't need to know everything. We know enough to know where we're going and what's going to happen. And so will we know everything? I don't think we need to. but no, we won't ever know everything.
I mean, Kyle said that we know enough, but he kept publishing new papers about tropical polar teleconnection more. Yeah.
Well,
well, it's great to advance knowledge, but that's what people want. But from a decision, from a climate change perspective, I think we know enough. That's all.
Yeah.
Yeah. So I think we come to a closure of this session. In fact, thank you all the panel members. It was very lively and vibrant. In fact, I learned a lot. In fact. So as we all understand, actually, in such a rapidly warming world, actually, that things are going to be different, and how these teleconnections play around is going to basically also decide our future, sort of thing. So I'm very grateful to all of you. In fact, we had an excellent, what you call audience. Actually, nearly about it touched 100 at one time. So we had a very, very vibrant audience, also raising a lot of questions. And I think it was a really timely topic to be taken up. Actually, and getting all of you people have been an extremely very happy thing for me, at least. Thank you so much. Thanks to all of you.
Yeah.
Thank you. Thank you.
Yeah.
Thank you, Dr. Thamban.
Thank you very much for
Thank you.
organising.
Yes,
Thamban.
yeah, thanks, Kyle. Thanks.
Thank you.
Thanks to
Professor.
Thanks to the SCAR. Thank you so much.
Thank you. Thanks.
Thanks.